Welcome to the second lecture of week 11. We will continue our discussion on micromechanics of failure of composite plies. In the previous lecture, we talked about the failure along the longitudinal direction, along tensile and compressive mode. Today, we will talk about the failure in the transverse direction and also the failure in shear mode. So, today we will start with transverse tensile strength of lamina, and this will derive using the mechanics of material based approach. So, for that let us refer to this schematic diagram. So, we have this is direction 1 and direction 2. Now, these denotes fibers, these rectangles with hashed lines, they denote fiber, and the empty rectangles are matrices. So, these matrices have these fibers have dimensions say d. So, d is the diameter of fiber, and the center to center distance between the fibers are s. So, we can say that the matrix the width here is s minus d. Now, we can consider just one combination here. So, we can say that this combination of this matrix and fiber, they just repeat. So, we can consider one such combination and study it here. So, again here we have this as d and this as s minus d, and this entire width is dimension is s. Now, if we load it along the transverse direction, if we have sigma 2 working, then both the matrix and fiber will expand along direction 2. So, we can say that the expansion of the fiber along direction 2 is delta f, and here along direction 2 of the matrix extension is this is delta m, and the total extension of the composite is delta c is equal to delta f plus delta m. Now, we know that for equilibrium here the stress in matrix and stress in fiber has to be same. So, sigma 2 stress in direction 2 is equal to stress in fiber is equal to stress in matrix. Now, delta f, the extension along direction 2 is equal to the dimension along extension along direction 2 of fiber is equal to the dimension of the fiber along direction 2, which is d, multiplied by epsilon 2 f, that means longitudinal strength and longitudinal strain of fiber along direction 2. Similarly, delta m we can write as s minus d, the dimension of matrix along direction 2, multiplied by epsilon 2 m, and likewise the total extension of the fiber matrix combination, which we can call as delta c, that is equal to delta f plus delta m, and we can write this as s, the total dimension along direction 2, multiplied by epsilon 2, that means the equivalent strain of the composite along equivalent longitudinal strain of the composite along direction 2. So, I can rewrite this as s into epsilon 2 is equal to d into epsilon 2 f plus s minus d into epsilon 2 m, and then we can write this as epsilon 2 is equal to 1 by s multiplied by epsilon 2 f d plus S minus d into epsilon 2 m. Now, if I look at this, so sigma 2 f is equal to sigma 2 m, this gives me epsilon 2 along fiber direction multiplied by epsilon 2 f, sorry, epsilon 2 f multiplied by E 2 f. E 2 f is the Young's modulus of the fiber along direction 2 plus E m multiplied by epsilon 2 m. So, they are same. So, from this I can express epsilon 2 f as E m multiplied by epsilon 2 m divided by E 2 f, and then I can substitute it here. If I do that, then what we get is epsilon 2 is equal to d by S multiplied by E m divided by E 2 f plus 1 minus d by S, and this entire thing is multiplied by epsilon m. So, now if we look at this entire quantity, the only parameter, only strength parameter this comes from this quantity epsilon m. So, when epsilon m reaches the ultimate limit, we can say that the ply has failed because of longitudinal stress along direction 2 in the tensile mode. So, if I take the ultimate value here, I can put the ultimate, I can call also this the ultimate limit of this. Now, I could have written epsilon 2 m in terms of epsilon 2 f also and did the same thing. So, we can write now that for failure epsilon 2 ultimate tensile is equal to d by S into E m by E 2 f plus 1 minus d by S into epsilon 2 epsilon m ultimate, because fibers matrices are isotropic. So, I do not need to put the do not need to put the direction. Now, this tells me that sigma 2 u ultimate, sigma 2 t ultimate, which we can write as f 2 t is equal to d by S into E m by E 2 f plus 1 minus d minus now for the corresponding failure stress, we can write sigma 2 t ultimate is equal to f 2 t is equal to E 2 multiplied by d by S into E m divided by E 2 f plus 1 minus d by S multiplied by epsilon m ultimate. So, this is how we find out the transverse tensile strength of composite ply. Now, let us discuss about transverse compressive stress, transverse ultimate compressive stress or transverse compressive strength. So, in this case the approach is same, because the fibers are because the load is in the transverse direction. So, there is no question of buckling of fiber shears. So, using the same approach we can find out the transverse compressive strength. So, there is no point in doing it once again. So, F2C we can just write E2 d by S Em by E2F plus 1 minus d by S, and here also we have epsilon m, but in the previous case the failure was in tensile mode. So, epsilon m T u, here it is in compressive mode. So, epsilon m C u. So, the matrix can have different failure stress for tensile or compressive mode, and accordingly we have to put T or C here, and that is the only difference. So, previously when discussing about the compressive strength along direction 1, we derived the ultimate tensile strain along direction 2. We did not derive it, we just used the formula, and here is the derivation for that. Now, we will talk about the failure in shear mode. Shear strength. So, for shear strength again we will refer to this diagram. We have seen that this is has a dimension, this has a dimension S minus D, the matrix part, and this has a dimension D, and the combination has a dimension S. And if this entire combination is under shear, so shear, then under shear the deformation would look like this. We know that the shear, when shear happens, this angle changes, they are no more 90 degree, and the angle that is formed here, that denotes the amount of shear strain we have, and because fiber and matrix have different shear modulus, the shear strain is different. Fiber is more stiff, so angle is less here, the shear strain is less. Generally matrix is less stiff, so the angle signifying the shear strain is more here, and accordingly we can write, we can draw it in the other side of it. So, this is how the deformed shape would look like. Now, there is shear deformation, the deformation due to shear, which we would be quantifying by the movement of this point from here to here, and that quantity we can write as delta m. Similarly, whatever we are seeing here, that is delta f, that means deformation due to displacement due to shear in matrix delta m, and the same thing in fiber is delta f, and the total quantity which we can see here is delta c. So, we can say that delta c is equal to delta m plus delta f. Now, we will follow the same approach like what we followed for the transverse, tensile and compressive stress. So, for that let us write delta m first. So, delta m is gamma 1 2 in matrix multiplied by S minus D. So, this is gamma 1 2 in matrix, gamma 1 2 in matrix, and this angle is gamma 1 2 in fiber. So, this angle multiplied by this dimension S minus D signifies the amount of deformation we have due to shear. Similarly, for fiber we can write delta F is equal to gamma 1 2 F into D. Now, we can write the total deformation delta C as an equivalent shear gamma 1 2 multiplied by S, the total dimension. So, now we know that delta C is equal to delta M plus delta F, and that gives me gamma 1 to S equal to gamma 1 2 of fiber multiplied by D plus gamma 1 2 of matrix multiplied by S minus D. So, this is one equation, and then we know that for equilibrium the shear in fiber tau 1 to F should be is equal to tau 1 to M, and that gives us G 1 to F, that means shear modulus of fiber in 1 2 plane multiplied by gamma 1 to F is equal to G M shear modulus of fiber, because matrix is homogeneous, I do not need to specify 1 2 here, multiplied by gamma 1 to M. So, from here we can find out gamma 1 to F as G M multiplied by gamma 1 to M divided by G 1 to F, and then we can substitute this quantity here, and with that we can write the gamma 1 to ultimate strain equal to D by S G M by G 1 to F plus 1 minus D by S into gamma 1 to M ultimate, and accordingly we can write the ultimate shear stress as tau 1 to ultimate is equal to D by S G M by G 1 to F plus 1 minus D by S into gamma 1 to M u multiplied by G 1 2. G 1 2 is the equivalent shear modulus of the composite. So, this completes our derivation of all these strength parameters of the ply, starting from the strength parameters of the constituents. So, the problem it asked us to find out the transverse compressive strength of a glass epoxy lamina, and the lamina has got 70% fiber by volume, and we have to assume that the fibers are circular and packed in a square array. The axial modulus of fiber and matrix are given to us 85 GPa and 3.4 GPa, and compressive strength of the matrix is 102 GPa. So, first we have to find out the ratio of D by S, because that is something that we will need in our analysis. So, for that we will refer to the relation that we derived in week 2 lecture number 1. So, at that time we saw that if the fibers are packed, if the fibers are circular and packed in a square array, then fiber volume fraction Vf becomes pi d square by 4 s square. So, please refer to week 2 for this relation. Now, Vf is known to us, which is 0.7. So, from here we can find out d by s as 4 Vf by pi to the power 1 by 2, and the value that we get here is 0.9441. Now, the compressive stress of the matrix is given to us. So, from there we have to find out the ultimate compressive strength of the ultimate compressive strain of the matrix, and that is epsilon m c u is equal to sigma matrix C u divided by E m, and sigma m c ultimate is given to us, that is 102. So, 102 GPa, 102 MPa, not GPa. So, 102 MPa and divided by 3.4 GPa, divided by 3.4 GPa, and the value that we get is 0.03. Now, we already derived the formula for epsilon 2 C ultimate, and that we know as epsilon m c ultimate into d by s multiplied by E m divided by E 2 f plus 1 minus d by s. And then if we put all these values here, then the value that we get is 0.281 into 10 to the power minus 2. So, E m we know 3.4 GPa, E 2 f. Now, here the fiber that is given to us is isotropic. So, this is also equal to the modulus along direction 2. So, if the fiber is not isotropic, then the we have to be specific about the fiber modulus, whether it is along direction 1 or direction 2. In this case it is isotropic, so it is same in both the direction. So, E 2 f as given to us, it is 85 GPa. Now, we can write the final quantity that is desired, sigma 2 Cu, which we denote as F 2 C, and that is equal to epsilon 2 Cu multiplied by E 2. Now, E 2 we have to find out. So, for that we know for that the relation that 1 by E 2 is equal to V f by E 2 f plus V m by E m. So, with this E 2 is found out to be, we can find out E 2 from here, and whatever the E 2 is we can put it here. The final answer, that is 29.14 MPa. So, with this numerical example I would like to conclude this lecture here. So, in these two lectures we have dealt with the micromechanics of failure of plies. So, we have looked into the individual constituent properties, their failure properties, and from there we have found out the equivalent failure parameters of the plies, and we have looked into one numerical example for that. In the next class what we will do is we will see that how we can determine whether our ply is failing or not based on these failure parameters that we have defined. So, let us end this lecture here. Thank you.